Hi students, in this video I'm going to discuss methods to find root of equations. Equations may be transcendental equation or a polynomial equation. So before moving to methods, so let us recall what we studied so far. You have seen that what exactly the analytical method. So generally analytical method gives the exact solutions to the problem within a finite number of steps. Later we studied what is numerical method and why numerical method. So generally numerical method gives the approximate solutions. So the question arises why we need numerical method. So generally there are some problems in applied mathematics and engineering applications. So we are not able to find analytical solution for such problems. So then numerical method is only the tool to find solution of such given equations. So therefore the numerical method is very accurate, efficient tool. In almost all the cases it is exactly comparable to analytical solutions. So later you have seen that what exactly the transcendental equations and polynomial equation, what are the simple root and multiple roots of the equation f of x equal to 0, and how to choose the initial conditions by using graphical method and by using the intermediate value theorem. Now let us move to the methods to find root of equations. Here equation may be transcendental equations or polynomial equations. Now let us move to bisection method. So it is a numerical method to find root of the equation. So this method is based on repeated application of intermediate value theorem. Value theorem. So what this theorem says that. So let us show it in the graphically. So you draw the coordinate system, x-axis, this is y-axis. So this is y is equal to f of x. So this equation crosses the x-axis at z. So you can observe that f of x is continuous in the interval ab, and moreover we can see that this point at x equal to a, f of a is positive, and at x equal to b, f of b is negative. Let us assume that f of x is continuous in the interval ab, and suppose a root of f of x equal to 0 lies in the interval ab, that is such that f of a into f of b is negative. So if f of a into f of b is negative, by intermediate value theorem says that there exists a root, let us call m1 in ab. Let us write either open interval or closed interval. So suppose there exists a root m1, approximate root m1 in the interval ab. So then we bisect the interval AB at m1, that is m1 is equal to, that is a plus b by 2. So let us take the real line with the interval AB. So you assume that the root lies between the interval AB. For example, what you have taken here. So the root lies between in AB, so that is a point z. So to find the approximate root of the equation f of x equal to 0, now what we do, just bisect the interval. Just take the sum and divide by 2. So we'll get middle of this interval, that is m1. So where m1 is equal to a plus b by 2. So once if you get the m1 by bisecting the interval ab, so how to find out f of m1. F of m1 may be positive, may be negative, may be 0. If f of m1 is equal to 0, so we can conclude that m1 is a root of the equation f of x is equal to 0. Suppose if f of m1 either positive or negative, doesn't matter. If f of a into f of m1 negative, the root lies between the interval a comma m1, in this interval. Or if f of m1 into f of b less than 0, then the root lies between the interval m1 comma b. Suppose if f of m1 into f of b is negative, so therefore the root lies between in this interval m1 comma b. Now suppose f of a into f of m1 is negative, then the root lies between the interval a comma m1. In this interval, you can observe that where m1 is the midpoint of the interval a comma b. Or if f of m1 into f of b is negative, then the root lies between m1 comma b. So in this interval, another half of the interval ab. You assume that f of a into f of m1 is negative. Either f of a into f of m1 is negative, then you have to bisect the interval a comma m1 at m2. m2 is equal to a plus m1 by 2. So you have to bisect the interval a comma m1, will get m2. So m2 is the midpoint of the interval a comma m1. So then we find f of m2. So another way, suppose if f of m1 into f of b is negative, if this is not negative, assume that. So what we have to do, we have to divide the interval m comma b at m2. Suppose if f of a into f of m2, sorry, if f of m1 into f of b is negative, then m2 is equal to m1 plus b by 2. So then you have to find out f of m2. So m2 will get here, m2 is the bisect of the interval m1 comma b, where m2 is the midpoint of the interval m1 comma b. So any one of the case will happen, so not both the cases here. Either the root lies between the interval a comma m1 or m comma m1 comma b here. Now, so let us assume that the root lies between the interval a comma m1. Will get m2 is equal to a plus m1 by 2. Now we find f of m2. F of m2 again may be positive or negative or is equal to 0. If f of m2 is equal to 0, therefore m2 is the root of the equation f of x equal to 0. Otherwise, f of m2 may be positive or may be negative. Now, so know the interval. So subintervals here a comma m2 and m2 comma m1 here, because you assumed that m2 is the approximate root lies in the interval a comma m1. Fine. So again there are two subintervals, that is a comma m2 and m2 comma m1. Suppose if f of a into f of m2 is negative, then the root lies between the interval a comma m2. Or if f of m2 into f of m1 is negative, then the root lies between the interval m2 comma m1. According to intermediate value theorem, if f of a into f of m2 is negative, then the root lies in the interval a comma m2. It means that so this interval contains the root. Or if f of m2 into f of m1 is negative, then the root contained in the interval m2 comma m1. Continue this procedure, you obtain the sequence of subintervals. Let us see it in the real line of the interval a comma b. So we'll get interval a comma b, let us take it as I naught. So we bisect the interval ab, we get m1. m1 is the midpoint of the interval ab. Suppose if f of a into f of m1 is negative, so therefore interval a comma m1 contains the root. Again you bisect the interval a comma m1, will get m2. Will get a comma m2 subinterval and m2 comma m1. Suppose if f of a into f of m2 is negative, so this is take it as I1. So I naught contains I1. Again you bisect the interval a comma m2, will get m3. m3 is the midpoint of the interval a comma m2. So if f of a into f of m3 is negative, so therefore the root contains in the interval a comma m3, take it as this is I2. I naught contains I1. I1 contains I2. Again you bisect the interval, will get m4. If f of a into f of m4 is negative, then the root lies in the interval a comma m4. So we'll get interval I3. Therefore I naught contains I1, I1 contains I2, I2 contains I3. it goes on. So therefore we continue the procedure, we get a sequence of subintervals like I0 contains I1, I1 contains I2, I2 contains I3, and so on. We can observe that each time of bisection process, the midpoint is taken as approximate of the root. After repeating the bisection process n times, either you will get real root of the equation f of x equal to 0, or will get small interval in of length b minus a by 2 power n. So now we will see the length of in, that is b minus a by 2 power n graphically. Let us take the interval AB of 1 unit. So bisect the interval at m1. So the length of the interval a comma m1, you can take it as off. So length of the interval m1 comma b, that is off. Suppose if f of a into f of m1 is with the product of f of a and f of m1 is negative, so again divide the interval at m2. So this length is 1 by 4, 1 by 4. Suppose if the root lies in the interval a comma m2, divide the interval a comma m2 at m3. So this length is 1 by 8, this length is 1 by 8. It keeps on going. So let us see that, compare with this formula here. So b minus a by 2. So when you divide the interval at m1, the length is b minus a by 2, the first time. When you divide the interval second time, that is b minus a whole by 4. You can observe that. So this length is 1 by 4. When you divide the interval again, once again, that becomes b minus a by 8. It means I can write b minus a by 2 cube. When you divide the interval third time, so we'll get b minus a by 2 cube. So similarly we can write b minus a by 2 power n is the length of in. Let us remark the bisection method. So first one is here, if m1, m2 and so on mn are the sequences of middle points of the interval an comma bn. If n is equal to 1, so m1 is the middle point of the interval a1 comma b1. So similarly m2 is the middle point of the a2 comma b2 and so on. So then mn converges to the xi, where xi is the exact root of the equation f of x equal to 0. So where m1, m2, mn are successive approximation to the root xi. So n represents the number of iterations. This is the first point. So generally this method requires a large number of iterations to achieve or to obtain a reasonable degree of accuracy. Accuracy for the root of f of x equal to 0. So we can find a number of iterations or nothing but number of bisection process by using the relation b minus a by 2 power n. So this is the length of the, let us say, in, where in is the sub interval of the interval AB. So let us take epsilon is the error, or that is xi minus mn, where xi is the exact root of the equation f of x equal to 0, where mn is the approximate root to the xi. So there is the error. If you assume that error is epsilon, so b minus a by 2 power n is a positive less than or equal to epsilon. So b minus a, this in, in contains the root, or that is any one of the point in this in is a root of the equation f of x equal to 0. Therefore, so there is a error in this length in. So let us take log on both sides. Log of b minus a minus log of 2 power n less than or equal to log epsilon. So this implies log of b minus a minus log of epsilon less than or equal to 2 times of, n times of log 2. So this implies n greater than or equal to log of b minus a minus log epsilon by log 2. So in this relation you can find out number of iterations. If you know the interval of the equation where the root lies between the interval a comma b, if you know a and b and error, so easily you can find out the number of iterations. Suppose if I consider the interval a comma b is equal to 0 comma 1, this implies a is equal to 0 and b is equal to 1. If you know the error, we can find a minimum number of iterations required for converging to a root. So let us draw in the table. So take the epsilon error and n is number of iterations. If we take the error 10 to the power of minus 2, so it requires 7 number of iterations to have a desired degree of accuracy to the root. Suppose if you take 10 to the power of minus 3 the error, so it requires 10 iterations. If you substitute epsilon is equal to 10 to the power of minus 2 for the relation 1, and b is equal to 1 and a is equal to 0, so we can find out 7 here. Similarly, we can find out n by using epsilon 10 to the power of minus 3, and b and a is 1 and 0. So if I take error is 10 to the power of minus 4, so it requires 14 number of iterations to get desired degree of accuracy of a root. So if we take the error 10 to the power of minus 5, it requires 17 iterations. 10 to the power of minus 6, it requires 20 iterations. So if I write 20 to the power of minus 7, it requires 24 iterates. So therefore, the drawback of the bisection method is it requires large number of iterations to obtain desired degree of accuracy to the root. Move to the problem. Find the real root of the equation x cube minus 5 plus 1 is equal to 0 using bisection method, and for forum 5 iterations. So the given equation is a polynomial equation. So you can think of analytical method. So to use analytical method, we can use the synthetic division method, otherwise factorization method. Suppose we want to use synthetic division method, so we need to find out one root by using inspection method. So that itself is very difficult task to find the first root. So once if you know the first root, easily we can reduce the second degree equation, we can use the quadratic formula. So finding first root itself is a very difficult task because the root itself is a real number. So therefore you can find a root easily by using numerical methods, that is bisection method. So bisection method is based on intermediate value theorem. So therefore we need a interval here. So now let us move to the solution. Let f of x is equal to, let us take x cube minus 5x plus 1. Now we need to find the interval AB such that f of a into f of b is negative. So this is the intermediate value theorem property. So let us take x is equal to 0. So f of 0 is nothing but 1. This is positive. For x is equal to 1, let us check f of 1 is equal to, so 1 minus 5 plus 1, that is equal to 3, minus 3, this is negative. So therefore f of 0 into f of 1 is negative. So f of 0 is positive and f of 1 is negative. Therefore product of f of 0 and f of 1 is negative. So therefore the root lies between the interval 0, 1. Take a is equal to 0 and b is equal to 1. So by using bisection method, let us bisect the interval 0 and 1. We get m1 is equal to, so that is a plus b by 2. A is 0, b is 1 by 2, that is 0.5. So m1 is 0.5. So this is a approximate root of the equation x cube minus 5 plus 1 is equal to 0. But here you have to perform 5 iterations of the bisection method. So now we have to find out f of m1, I mean f of 0.5. Here f of 0.5 is here, minus 1.375. So substitute x equal to 0.5 for the function f of x equal to x cube minus 5x plus 1, we get minus 1.375. So this is again negative. F of 0.5 is negative, and search for which value of x f is positive. Here f of 0 is positive. F of 0 is positive and f of 0.5 is negative. It means our interval here 0 comma 1. So here f of 0 is positive, f of 1 is negative. So we bisected the interval, we got 1 by 2, 0.5. So again f of 0 is positive and f of 1 by 2 is negative. Therefore root lies between the interval 0 comma half. Thus the root lies between the interval 0 comma 0.5, because f of 0 is positive, f of 0.5 is negative. So again we have to bisect the interval 0, 0.5. We get m2 is equal to 0 plus 0.5 by 2. So we get it 0.25. So then you find f of m2. F of m2 is equal to f of 0.25. F of put x equal to 0.25 for the function f of x equal to x cube minus 5 plus 1. So we get minus 0. 0 minus 0.2343 is again negative. So you can observe that f of m2 is negative, f of m1 is also negative, f of 1 is also negative, f of 0 is negative, positive here. So here 0.25 comes here, so 0.25 here. So f of 0 is positive, f of 0.25 again it is negative, therefore root lies between the interval 0 and 0.25 here. Since f of 0 into f of 0.25 negative, therefore root lies between interval 0 comma 0.25. Again you have to bisect the interval 0 comma 0.25. We get m3 0 plus 0.25 by 2. So we get it 0.125. So then we find out f of m3 is here, f of 0.125, f of 0.125 is again it is a positive here, 0 point, that is the f of 1.25 is f of 0.125 is 0.37695 is positive. F of 0.125 is positive. Here f of 0.25 is negative. Here you can observe that here. So here we consider the interval 0, 0.25. So f of 0 was positive, f of 0.25 is negative here. So when bisected the interval, we get 0.125. So we found that f of 0.125, that is positive. So this is at x equal to 0.125 is f of x is positive. So f of 0.25 is negative. Therefore the root lies between 0.125 and 0.25. Since f of 0.125 into f of 0.25 is negative, because f of 0.125 is positive, f of 0.25 is negative. So therefore the root lies between the interval 0.125 comma 0.25. Again we bisect the interval 0.125 comma 0.25. We'll get m4. m4 is 0.125 plus 0.25 divided by 2. So we'll get it 0.1875. So we find f of 0.1875. So again this is a positive. So here you can observe that f of 0.1875 is positive and f is negative at x equal to 0.25. Here you can observe that in interval. So 0.125 and 0.25. When you bisect the interval 0.125 and 0.25, we get 0.1875. At x equal to 0.1875, f is positive. At x equal to 0.25, f is negative. Therefore product is negative. So therefore the root lies between here you can observe that f of 0.1875 into f of 0.25 is negative. Therefore the root lies between the interval 0.1875 comma 0.25. So again we bisect the interval, we get m5. So that is 0.1875 plus 0.25 divided by 2. We get 0.21875. We find f of 0.21875. So we get this is negative. Since f of 0.1875 is positive, so therefore f of 0.21875 into f of 0.1875, again it is negative. Therefore the root lies between the interval 0.1875 comma 0.21875. Again bisect the interval, we get m6. m6 is the 0.1875 plus 0.21875 divided by 2. So we get it 0.203125. Therefore the approximate root is 0.203125.